Hey guys, this section we're jumping to section 11.1, and the title of the section is Systems of Linear Equations. So in the last section we were talking about lines. We talked about lines in general form, in slope-intercept form, and in point-slope form. And so let's put down a couple lines in standard form. And so this is kind of an allusion to something that we briefly talked about, which is parallel and perpendicular lines. Essentially what we're doing in this section is, what are the possibilities if you draw two different lines on the same graph, right? Okay, so what are the three types of lines that are possible? Well, I guess you could break it into four. We have positive slope lines, negative slope lines, vertical lines, and horizontal lines. Okay, so the idea here is that we're drawing two different lines on the same graph. So what are the possibilities and what are the solutions to this set? Well, the solutions are the ways in which both lines intersect each other. And so if I draw two lines, right, like these pair, they have one intersection here, right? They only cross at one point. So the three possibilities are that they cross at one point, like this picture. They never cross. And what kind of lines never cross? Well, parallel lines never cross, right? Because they're starting at different positions and have the same slope. So these will have zero solutions, or no real solutions is something you may remember in algebra. And the other pair, what's the other way that lines can intersect? Well, assume this is the first line and the second line is just right on top of it. So essentially what you have is the same line twice, and that has infinitely many solutions, or you might have seen something like all real numbers as the solution. So for these systems of equations with two variables, right, we just have the variables x and y. Essentially what we're trying to do is just find how many different points on the graph do these lines intersect. And so we have a few different techniques. In this video we're going to cover the elimination method. The book calls it the addition method, so you can call it whatever you want. And so what's the idea here? Well, when we have two different variables, we can't really solve for two different variables. So what do we have to do? We have to eliminate, right, one of the variables. Sorry, I have to keep scrolling up seeing what the equation was. And so the idea here is that we're going to add these equations together, and that's why the book calls it the addition method. We're going to add these equations up so that one of the variables gets eliminated. Now you can see in our example here that if we add these equations together, right, the x's to the y, the x's to the x's, the y's to the y's, the numbers to the numbers, the y's have the same quantity but different signs, right? One's positive, one's negative. So when we add these variables together, the y's are going to cancel. Okay, so let's go ahead and do that. And when we do that, we get a new equation. 2x plus 3x is 5x. Y negative y makes 0y. So we can just write 0y. 15 plus 5, and that gives us 20. And so what's the equation we're left with now? Well, it's an equation of only x's, right? An equation of one variable. And these we should be pretty comfortable with solving now. We just want to isolate x. And that tells us that x is equal to 4. Okay. And now that we have x is equal to 4, what we can do is take this number and plug it back into either one of these two equations, whichever one you want, and then that will tell you what y is equal to. So let's just choose the top one for no particular reason, and we're going to replace the x with the 4, because we know that x is the same thing as 4. And 2 times 4 is 8, plus y is equal to 15. We subtract 8 from both sides. And what are we left with? Y is equal to 7. So if these are our two equations, it's not that just x and y, x is 4 and y is 7, but these two lines intersect at the point 4, 7, right? So that's the idea. This looks like 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, right? And so both of these lines intersect at this point here. That's like the visual representation of what we're doing. So let's do another one really quickly. Well, it doesn't have to be super quick. I'm just making up numbers here, so things may get ugly. Okay, so we want to, remember, since this is called the elimination method, we want to add these equations up so that one of the variables gets eliminated. But as you can see, we don't have the same case that we had before, where here the y's were already opposite signs and the same value, so when we added them, they disappeared. We don't have that case here. So what we need to do is we need to multiply one of these equations or both of them by a number, so that when we do, they will end up with the same number, opposite sign, right? Additive inverses. So since this is just a regular y, it's just one y, I'm going to choose this equation and I'm going to multiply it by -2. And so that's going to give me the equation -6x minus 2y equals -8. Okay, essentially what we're doing is we're multiplying the left side by -2, but as long as we multiply the right side, right, as long as we do to the left what we do to the right side, we're not changing the equation, so this is totally kosher. I'm just going to write the original first equation up on top. And now what we're going to do is we're going to add like before, but now we have this relationship that we wanted where the y's are essentially going to disappear. So 2x and -6x, that makes -4x, and then 10 plus -8, that gives us +2. We divide both sides by -4, and that gives us x is equal to -2/4, which is equal to -1/2. And I know the 4 was negative here, but -a/b is the same as a/b, which is just the same as -a/b. It doesn't really matter which number you give the -2, because it's the entire fraction that's negative, right? So that's why I just assign the negative to the 2. Typically, I like giving the negative to the top number. But so x is equal to 1/2. Cool. And so now that we have this, we can plug this into either one of our equations. And I'm going to plug it into this equation right here because it has a lot of 2's in it. So 2 times -1/2 plus 2y is equal to 10. And the 2's cancel, right? So we get -1 plus 2y is equal to 10. We add 1 to both sides. And what do we get? 2y is equal to 11. And we divide both sides by 2. And that tells us y is equal to 11/2. So you can see that the numbers aren't quite as pretty in this problem, but we know that these lines intersect at one point, right? Because we only got one pair of points as an answer, and it's the point -1/2, 11/2. Okay, so let's quickly scroll up. And so we've seen in two different cases what one point looks like as an answer, right? What does no points, like no solutions, look like? And what does all ordered pairs look like, or all real numbers? So we already saw this case, so we know what that looks like. Well, what does no solutions look like? Well, let's say we have 2x plus 2y is equal to 2. And this one, let's call it 2x plus 2y is equal to 3. And you see that these equations look very, very similar. It's just the numbers that are different. And so if we multiply the bottom one by -1 and we multiply across, we're going to have, I'm just writing the top equation again. The bottom equation becomes negative 2x minus 2y is equal to negative 3. We add these equations together, right? And all of this is everything on the left side here is just going to go away. It's going to become 0 is equal to 2 plus negative 3, which is negative 1. And this should throw up some red flags in your head, because is 0 ever equal to negative 1? No. So this is a false statement, and no number that we could pick for x and y, will ever make this true, right? So that's why we can say no real solution. So what does this look like? Well, this is the parallel line example, and if we were to put this in slope-intercept form, this equation looks like y equals negative x plus 2, and this one looks like y is equal to negative x plus 3, not 2, but 1, excuse me, and 3/2, yeah. So you can see that these lines have the same slope, right? They have a rise over run of negative 1, but their y-intercepts are different. So two lines that have different y-intercepts, one at 1, one at 3.5, that rise and run at the same rate, they're going to be parallel lines, and of course these are never going to intersect, which is why we have no solutions, and it gives us a contradiction, a statement that is never true no matter what x's and y's we choose. Okay. All right. So what does it look like when we have all real numbers? Well, remember that this was the case when we have one line and the second line is just the same line on top of it. So the only way that you're ever going to get this is if you have the same line twice. So assume the first equation is 2x plus 2y is equal to 4, and the second equation is 4x plus 4y is equal to 8. Notice that these two equations are basically the same. It's just that the bottom equation has been multiplied by 2, right? So if you multiply the top equation by negative 2, right, because remember our goal is always to get things to cancel out, we'll get negative 4x minus 4y is equal to negative 8, and then the bottom equation is 4x plus 4y is equal to 8. And when we add these equations together, we get 0 on this side and we get 0 on the other side. So what this is telling you, this is a true statement, right? And this statement is always true no matter what xy pairs you choose. You could say x is 0, y is 100, and this will still be true, because at the end of the day, the only thing that matters is that 0 is 0, which is basically saying that you're just going to have the same line drawn on top of each other, right? And these lines are always going to intersect. Okay, cool. So I'm going to cut the video here, and it's going to be the same idea in the next one. It's just that we're going to be using a different method to solve it.